Think back to 2005 for a second. If you wanted a computer to understand language, you had to get a bunch of linguists to hand code thousands and thousands of grammar rules. I mean, it was brilliant, but it just didn't scale. So what happened? Well, we stopped teaching the rules and we just let the machines read, well, the entire internet. And by 2023, for most things, language was basically a solved problem. But robotics? Yeah. Robotics today is still very much stuck in its 2005 moment.
And this slide right here just nails the analogy. On the left, that's the old, brittle, hand-coded way we used to do language AI. And on the right, that's robotics. Right now, today, we are still manually programming the physics for how a sponge squishes or how water pours. It's the reason a factory robot can do the same thing a million times perfectly, but a robot in your home just completely freezes up if you move a chair. But a new class of AI, called the world model, is about to change all of that.
So here's the absolute heart of the issue. Robotics is facing a massive, massive data bottleneck. You see, language models had the entire internet of text to learn from. But where do robots get their experience? There's no internet of physical experience for them to download. We have to build it all from scratch. And the old way of doing things, these hand-coded simulations, they just can't capture the messy, chaotic, unpredictable nature of the real world.
All right, so how do we break out of this 2005 moment and get to a real robotics revolution? Well, here's the plan. We're going to start by exploring the data desert that's been holding everything back. Then we'll get into the really clever solution, world models. After that, we'll see how robots can literally train inside their own imagination. And finally, we'll get real about the hurdles we still have to overcome and what that ChatGPT moment for robotics is actually going to look like. Okay, first stop, the robot data desert. And let me be clear, this isn't just some small technical issue. This is the fundamental barrier that has kneecapped general-purpose robotics for decades. You can't just, torrent the physical world.
And just to put a number on this problem, a really big number, the industry is projected to spend over $3 billion just trying to create this data. That's how desperate the field is for a deep, rich data set of physical interactions. The financial stakes are absolutely massive because, well, the potential payoff is even bigger.
So where is all that money going? Well, it's going into these incredibly slow, incredibly expensive, and really specialized methods. You've got people literally putting on VR suits to puppeteer robot arms. It's called teleoperation. You have specialized gloves and grippers that try to capture not just what something looks like, but what it feels like to touch. It's painstaking work, and it produces way, way less data than the language models ever had to play with.
So this data desert, it feels kind of hopeless, right? An impossible hurdle. But what if there's another way? What if the biggest data set of physical data on the planet has been hiding in plain sight this whole time? I'm talking about internet video. And that is the promise of the world model, the hero of our story.
Okay, so what exactly is a world model? Honestly, the best way to think about it is like a toddler. A toddler learns that a ball will roll off a table not because they solved Newton's equations, but just by watching stuff happen over and over and over. A world model does the exact same thing, but it watches millions of hours of YouTube videos, cooking shows, sports, car crashes, you name it, to build its own internal intuitive feel for physics. Now this slide, this is the secret sauce. This is the key insight that makes the whole thing click. A robot actually needs two different types of knowledge. First, on the left, there's world knowledge. This is the universal stuff, the rules of physics. It's the same for you, me, or a robot, and it can be learned from all that video out there. Then on the right, there's action knowledge, which is just how its own specific body and motors work. And here's the absolute game changer. It turns out you need surprisingly little of that second part.
And if you want proof, this graph says it all. I mean, just look at the data Meta used for its VJPA2 model. On the left, you have this mountain of data, over 1 million hours of general internet video to build that base world knowledge. And on the right, that tiny little sliver, just 62 hours of actual robot data. That's it. That incredible imbalance, that's the whole magic trick right there.
So does it actually work? Oh yeah, it works. The results are frankly stunning. With that tiny amount of specific robot training, the model hit an 80% success rate on tasks it had never even seen before. It was generalizing its intuitive physics to brand new situations. This is what we call zero-shot performance, and it is a massive, massive leap for the entire field. So this physical intuition, it unlocks one of the coolest, most powerful ideas in AI right now, letting a robot practice inside its own AI-generated imagination. This could completely change how we train robots, and it brings up a pretty big question. Are we about to see the death of the traditional simulator?
And this slide lays out the difference perfectly. On the one hand, you have the old way, traditional simulators. They're built by engineers, the physics is all hand-coded, and they're only as good as the rules you give them. On the other hand, you have world models. Their understanding is learned from video, and this is the crucial part, they scale with computing power, not with how many engineers you can hire.
And you really see where the old simulators just fall apart when you get to the messy stuff, manipulation. They're fine for rigid things, like a robot leg walking on a flat floor, but folding laundry, squeezing a sponge, tearing a wet paper towel, you just can't write code for the infinite ways those things can happen. It's basically a dead end for that kind of problem.
And this quote, man, it just sums it all up. There's this idea in AI history called the bitter lesson. And it basically says that time and time again, the approaches that can just throw massive amounts of computation at a problem almost always win in the long run. And that's exactly what world models are built to do for physics.
Okay, so it's easy to get excited and think world models are here, problem solved. But we gotta be real, we're not quite there yet. There is a huge gap between a cool research paper and a robot that can actually tidy up your messy house. So let's talk about that. Let's talk about the reality gap.
And believe me, this isn't some niche academic project. It is an all-out race. You've got all the big names, NVIDIA, Google, Meta, Wave, pouring insane resources into this. We're talking models with over 10 billion parameters being trained on tens of thousands of the best GPUs money can buy. The scale is just astronomical. But the challenges? They're pretty big too.
So, if we boil it down, there are three main hurdles we need to clear. First, something called spatial inconsistency. Basically, the AI can forget an object exists if it looks away. Second, video is blind. It can't teach a robot how something feels, the force, the friction, the texture. And third, the big one, cost. Right now, running these things is just way, way too expensive for you or me.
But the good news is, people are already tackling these problems head-on. To fix that whole forgetting where things are problem, some new approaches are using a kind of stable, 3D digital skeleton of the room. This makes sure that objects stay put, giving the AI true object permanence. The way a baby learns a toy is still there even after you hide it. And that brings us back to the elephant in the room, cost. Some industry sources estimate that to run a single robot on a high-end model like Google's Genie 3 could cost around $100 an hour. Yeah. So before a robot is helping you with your dishes, that number needs to drop by a factor of like 1,000. It's a huge engineering challenge for sure, but hey, we've seen this movie before with large language models. So yeah, there are still some very real gaps, but make no mistake, we are undeniably at the start of a whole new era for robotics. We are standing right on the threshold of its ChatGPT moment.
I mean, if you just look at the history of AI, the pattern is unmistakable. First, for computer vision, learned models beat hand-designed filters. Then, for language, learned models beat hand-coded grammar. And now, for physics, learned world models are beating hand-built simulators. It is the same playbook, running all over again, but for the first time, it's for the actual physical world.
And what does this future actually look like in our homes? We're not just talking about a robot that can move a block. We're talking about a robot that has, well, an intuition about the world. One that can tidy up a messy room because it has object permanence. One that can finally fold laundry, the holy grail, because it actually gets the physics of cloth. A robot that can help you cook because it knows how pancake batter is supposed to pour. And all of this leaves us with one last provocative question to chew on. For decades, the conversation around robotics has been about hardware, building better hands, stronger motors, better legs. But what if that's not the main problem anymore? What if the hardware is finally good enough? Has the entire challenge of general-purpose robotics shifted? Is it no longer a hardware problem, but now just a data and a cost problem? And if that's true, how long until we solve those too?